Load tracing. Early in the structural design phase of a project, an initial assumption is made by the designer about the path across which forces travel in a structure, usually from top of this structure to the ground or foundation. Loads or forces that we have in a structure travel along what we call load paths, and the analysis method is referred to as load tracing. So, for example, in this slide, you see the load path through a simple wood framed structure. The analysis for load tracing is usually starts at the top of the structure, so roof, with the smallest members actually picking up the loading, and then we proceed by tracing the loads through each collecting member. So we look at the dead load and live load of roof, calculate how much load is transferred from roofing system to bearing walls. So that's our first level. Second level, we add the load transferred from roofing system to dead load and live load that we have in the bearing walls. The total is transferred to the flooring system that we have. Then we also need to look at dead load and live load in the flooring system. And finally, we can calculate the total load transferred to the ground or to continuous foundation. The reactions of each member to its loading becomes forces on the members supporting it. So, for example, we have a beam supported by columns. We have loading on our beam and we calculate reactions. So these are the reactions. So we have the reactions of our beam. These reactions becomes forces applied to the element supporting the beam, which in this case it can be a bearing wall or a column. So the same load, same magnitude with the opposite direction is the load transferred from beam to columns or bearing walls supporting that beam. So that's why we need to look at the load applied to the element, calculate the reactions, same magnitude in the opposite direction is transferred to the element supporting our beam. Simple determinate structures can be thoroughly analyzed using free body diagrams in conjunction with the basic equations of equilibrium. Let's look at our simple wood framed structure here again, just to review that we have roof sheeting and a snow load, so we need to add live load and dead loads that we have in our roofing system. We also have rafters and ceiling tie. We calculate these reactions on both sides. So we have the reactions. Reactions are the forces transferred to the next element, the element supporting our roofing system. Bearing walls are supporting our roofing system. So the same magnitude with the opposite direction is transferred from roofing system to bearing walls. So the reactions that we see in our rafters are the loads applied to our bearing wall. Then we need to add dead load of our bearing wall. So the wall by itself, it has a dead load. So we need to add dead load of wall to the load transferred from the roof to have the reactions. These reactions are transferred to flooring system, and from the flooring system to the ground or to the continuous foundation. But when we get to flooring system, now we need to look at the dead load and live load. The dead load, we have structural elements. We have floor sheeting, rim joist, floor joist. We also have live load, which can be furniture, occupancy load, so everything. We need to calculate all of these and then calculate their reactions. Then we add all of them together, this and this. Okay, it goes on top of the all of the loads that we have, the total transferred to the continuous foundation. The path that we followed is the load path, and the analysis that we do is called load tracing. How loads are transferred. Gravity loads usually trace from top down to their resolution at the foundation. So that's why we start from roof, move along different elements in a structure to the ground. So again, if we look at this example, we have a snow or roof live load for non-snow areas. That's our live load. Then it's transferred to the bearing wall or columns to the ground. Also, when we get to the flooring system, we have to add live load and dead load of our flooring system. And then we add everything together to find the total ground reaction. So the path is from top to down until we get to the ground reaction. Different types of loads. I want to review this. We have point load or a concentrated load. So something like this, which usually has a unit of pound. This is an example of point load. For example, where we have a joist connected to a beam. Here, if we look at the beam, if this is our beam, where joist is connected to the beam, we have a point load. Then we have the loads acting along a line. For example, floor on a beam. So we have a beam and we have a flooring system. Then we have a linear load. Or another example is when we have a bearing wall sitting on a beam. This one is usually pound per linear foot, or PLF. So this is a linear, uniformly distributed load. And then we have the loads acting on a surface or on an area, which is a snow on a roof, dead load of a roof, occupant on the flooring system. These are all example of load along an area. So this is an area load, and the unit is pound per square foot. And then finally, another type that we have is called distributed by tributary area. So we will talk about this more, but we have an area, for example, flooring system. And this flooring system is supported by two beams. We say that the load is divided between these two beams. So half of the load, this is transferred to this beam, and the other half is transferred to the other beam. So two beams supporting an area load. The load is divided between these two beams. It's carried by these two beams. These areas are called tributary areas. And the distance here is tributary width. Member hierarchy is also very important. You need to make sure that you are following the load path carefully. For example, in the flooring system, flooring spans between joists. Joists span between beams. Beams span between girders, and girders span between columns. So if we look at the plan in this slide, we have level 1, decking or sheeting. Then we have beams, joists, girders, and finally columns. So you need to make sure you pay attention to the connections, to the details, and follow the correct load path. As I mentioned earlier, in order to perform the load tracing analysis for structurally stable examples that we have, we will use free body diagrams, FBDs, and equations of equilibrium. So let's look at free body diagram for the elements that we have in this plan. We start with decking and sheeting. This is our so we have the free body diagram. This distance is decking span. We have the area load on the decking, and as you can see, uniform area load, live load plus dead load, in pound per square foot, which we show it using PSF. So whenever we have a surface and an area load, the unit is PSF. We calculate the reactions. These are the reactions. And as we talked about it earlier, the reactions are the forces or loads transferred to the supporting member. So we have beams supporting deck. So the next free body diagram is the free body diagram, FBD, of the beam. And this distance is beam span. and the reactions are forces applied or transferred to the beam. And now you see that on the beam we have the load in pound per foot, or PLF. So we have the load, we have the length of the beam, we calculate reactions. So now we calculate reactions here. And these reactions are the loads or forces transferred to girders supporting our beams. So these are the loads transferred. And now we have point loads, which are in pound. At each point where a beam is connected to the girder, we will have a point load. So now this is our girder. This is the girder span. And now we calculate the reactions here. Again, reactions here, when we do the calculation, are the loads transferred to columns supporting girders. So this is the load transferred to column. This is in pound. If we have dead load of column, we can add that to the load transferred to the column, and we can have our final ground reaction. This is the load transferred, for example, to the spread footing supporting this column. This is called load tracing. Here you can see another example for load path. Again, it's very important that we select the correct load path. So we have an area, decking. This is our deck with an area load. Deck with an area load, which will be in PSF, pound per square foot. The decking that we have, so here we calculate live load and dead load. It's supported by beams. So we have, that's our load path. Deck is supported by beam, and beam is connected to different color girder. So we will have a linear load on our beam, or distributed load, which will be in PLF, and where it's connected to the girder, here we will have a point load or concentrated load in pound. So beam to girder, and then our girder is connected to the column. So here we will have another point load in pound. And that is our load path. From decking to beam to girder to column. So you need to pay attention to the connection details that we have. You see that here, beam is connected to the girder. We may have a different connection where our beam can also be connected to the column. Then it directly goes to the column. Tributary area. The tributary area is an area that corresponds to the load on a member. If geometry and loading is symmetric, then load paths and reactions are also symmetric. That's a note. This concept typically considers the area that a member must support as being halfway between the adjacent similar members. This is the example that I talked about earlier. So if we have a surface with area load and then it's supported by two beams. The load is divided. Half of the load is carried by the right beam, half of the load is carried by the left beam. This area is called tributary area, and it's when we have a symmetric system, it's halfway between the adjacent similar members. The adjacent similar members here are the two beams that we have, and tributary area is halfway between these two beams. Tributary width is half of the distance. So this is tributary area. And half of the distance between the adjacent similar members is called tributary width. Let's look at an example to better understand the tributary area, tributary width, and the use of tributary width to calculate the load transferred from an area to supporting elements. So this example, we have an area. The general load over the entire deck area is a uniform 50 psf. So we have an area, and on this area, our deck, the load, the area load is 50 pounds per square foot. This area is supported by 4 beams. 1, 2, 3, 4. And the spacing between the beams is 4 feet. So the adjacent similar members supporting the deck are our beams. and the distance between the spacing between the beams is 4 feet. We said that tributary area in a symmetric system is half of the area between two adjacent similar members. So if we look at beam A, this is A, it only has one adjacent member, which is beam B, along line B. So tributary area for beam A is half of the distance, half of the area between A and B. This is tributary area. And tributary width for A is half of the distance between A and B, which is 2 feet. So again, if we look at this is beam A, and the only adjacent member to beam A is beam B. The distance between two is 4 feet, so half of that distance is 2 feet. So tributary width for beam A is 2 feet. Now, if we look at beam B has two adjacent members, beam A and beam C. So half of the distance between B and A plus half of the distance between B and C. If I want to show it on this plan, so if we look at beam B, there is half of the area on the left side and half of the area on the right side. So it's 2 feet on the left side plus 2 feet on the right side. So tributary width for beam B is 4 feet, which is 2 feet on the left side and 2 feet on the right side. For beam C, we have the same thing. For C, if we look at C, it's half of the distance. It has two adjacent members, B and D. So tributary width for C is 4 feet. And then finally, if we look at beam D, it only has one adjacent member, which is beam C. So tributary width for beam D is 2 feet. Okay, so let's go over the example again. Tributary width contributing to the load on beam B. Again, beam B is this one. And it has two adjacent members, A and C. The tributary width contributing to the load on beam B is half of the distance or Planck span between A and B, half of the distance between A and B, plus half of the distance between B and C. Same thing for beam C. So for B or C, we have half of the distance on the left side and half of the distance on the right side, which gives us a tributary width of load on beam B or C is 4 feet. And then, so this was for B or C. And then for A or D, there is only one adjacent member. So tributary width is half of that. Tributary width for edge beams, which we only have one adjacent members to them, is 2 feet. Okay, so now how can we calculate the load transferred to the beam? We said that tributary width of load on beam B and C is 4 feet, on beams A and D are 2 feet. But how much is the load? What is the percentage? What is the contribution of area load to each of these beams? We have this area load, 50 PSF, pound per square foot. You need to multiply this number by tributary width to calculate the load transferred to each of these beams. So if we look at beams A and D, where we had a tributary width of load on them as 2 feet, then 50 PSF times 2 feet, which gives us 100 pounds. If we are looking at the middle beams, where we have two adjacent members and a tributary width of 4 feet, then the load on these beams are 50 PSF times 4 feet, or 200 PLF. And pay attention that PSF times feet gives us PL. Now we can do the free body diagrams for beams B and C. So for beams B or C, we have the beam. The span length is 16 feet. And the load is 200. So we have 200 PLF. We can calculate the reactions. Reactions are equal to load that we have times length of beam divided by 2, which is equal to 1600 pounds. So this is how much load is transferred from beams B and C to the member supporting these beams. We can do the same thing for beams A and D. But this time, the load on A and B is 100 PLF. And again, we can do the calculations for reactions. The load, linear load that we have, times length of beam divided by 2, which gives us 800. So if we had the next member supporting out beams, we actually had the load transferred from these beams to the member supporting the beams. You can pause the video and try to solve the example by yourself before I go over the answer. So there is a small change. In this example, now we have an area load of 60 psf. I will go over the answer now. Tributary width of load on beam B and C. Beams B and C. B and C, where we have two adjacent members. So tributary width is 4 feet. And tributary width for load on beams A and D, where we have one adjacent member. So tributary width is 2 feet. Now we need to calculate the load on each beam. So for beams, edge beams A or D, it's the load, the area load that we have, which is 60 psf times 2 feet, which gives us 120 plf. For the middle beams, it's 60 psf times 4 feet, which gives us 240 plf. So now we can draw free body diagram. We're going to do FBD for B and C. And the free body diagram for A and D. And then calculate the reactions. Here we have 120 pound per foot times 16 feet divided by 2, which gives us 960 pounds. And here we have 240 times 16 divided by 2, which gives us 1920 pounds. So we just went over all of these. For A and D we had 120, and here we have 240, and then we did the free body diagram. Okay, let's look at other examples for load paths. Here we have examples for different wall systems. The first one is uniform wall load from a slab. So we have a concrete slab that has an area load. It's supported by concrete or reinforced masonry wall. Half of this load, this is the tributary area. Calculate the load transferred to the wall, and then from, if we add weight of the load of wall, we can have the ground reaction. So it's from concrete slab to wall to footing. That's our load path. The second example for a wall system is uniform wall load from roof or floor joists. So we have roof or floor joists at close regular spacing. We calculate the load on each of these joists, calculate reactions, and then calculate how much is transferred to the bearing wall. So we have from joist to the wall to concrete footing. This is our load path. And we will have a uniformly distributed load transferred from the bearing wall to the footing. And the third one is when we have beams spaced at wide intervals. So the path is still the same from beam to bearing wall and from bearing wall to the footing. But there is a difference between when we have beams spaced at wide intervals compared to when we have joists at close regular intervals. You see here we have a uniformly distributed load transferred to the footing, but when we have beams spaced at wide intervals, we have a higher concentration of load where beams are sitting on the bearing wall. So if you look at the load transferred to the footing, you see that instead of a uniformly distributed linear load, we have a triangular load with a higher concentration or a higher magnitude under the beams. The next example is for stud walls with a window opening. So we have load from rafters or joists, studs, and concrete footing. So from rafter to the studs to concrete footing. Again, a note here for this detail is that when we have a window opening and a header, then we will have a higher magnitude or a higher concentration under the window opening. It's the same thing when we have pilasters supporting concentrated beam loads. Again, if the beam load is high, then we need support and we may use pilasters. So the load path is from beam to pilasters to footing And in this case, we will need an enlarged concrete footing to support these higher loads with higher magnitude. Now let's look at examples of load paths for floor systems. The first one is one-level framing. It's not a very common framing system. Relatively long-spanning decking materials may transmit roof or floor loads directly to bearing walls. So it's consisted of two levels. We have precast concrete planks or decking, and then we have bearing wall. In this system, width of a plank is the tributary width. So tributary width is equal to the width of a plank. Then we can do free body diagram for our plank. So we have one plank here, we have length of that plank, we have dead load and live load, and it's an aerial load. It's pound per square foot. We calculate the reactions, and these reactions are the loads transferred to the bearing wall. The next system is a two-level framing system, which is a very common floor system that uses joists to support a deck. Efficient structural sections in wood and steel joists allow relatively long spans between bearing walls. So again, we have deck, but the decking is supported by joists, and then load is transferred from joists to bearing wall. So we will have a free body diagram for our deck. For each joist, if it's a single joist, it has two adjacent members. So tributary width of a joist is half of the distance on the left side and right side. So first we do free body diagram for our decking. Again, the load is in PSF. The reactions are transferred to joist. So each one transfer a load to the joist. Then we can draw the free body diagram for a joist. So we look at a joist and we do free body diagram of that joist. Load is now in PLF. Then we calculate these reactions, and the reactions are the loads transferred to bearing wall. The next system is a three-level framing system, buildings requiring large open floor areas, free of bearing walls, and with a minimum number of columns. In these cases, we need the long span capability of joists supported by trusses or girders. So we have one more level here. We have decking, beam, joist, girder, and then columns. So we need to do free body diagram for all members. We start with free body diagram of decking with an aerial load. Reactions are transferred to the, so we have aerial load transferred to joists. This is PLF. Then we calculate reactions. These are transferred to the beam. Joist loads are transferred to the beam. Then we can calculate the reactions, which are transferred to the girder. So this is our girder, and we have the load from beams. And finally, we can calculate the loads transferred to the